This video is what I consider the meat of this quantitative methodology chapter sandwich, data analysis. Personally, this is what I do most of the time, right? I work on the data analysis. This is the good part. So first thing they're going to ask you is, which test are you going to run, right? Which statistical analyses will you be using to test these hypotheses? And as you probably well know, there's a lot of them out there. But what I try to suggest is try to use what I call the cafeteria analyses. Nothing fancy, but they are good, right? They're standardized, but a lot of people use them, right? They're the most popular ones, and it would be the t-test, the ANOVA family, correlations, regressions, and of course the chi-squared test. Those are the big five I consider. So I strongly suggest you stick with those five, but if you want to do something fancy, it's your paper, so go ahead and do it. But whatever test you run, make darn sure that you check the assumptions for each and every test. Every test has different set of assumptions, except for the t-test and the ANOVA, right? They're both basically the same assumptions: normality, homogeneity, variance, and independence of observation. But again, the correlations and regressions have a lot, and chi-squared doesn't have many, but just check the assumptions, right? They're going to want you to check the assumptions. And after you've chosen the test, they're going to ask you, how do you know you're using the right test? This is that decision tree practice that they test you on, right? How do you know you're using the right test? Okay, next, you gotta tell your readers what kind of uncommon methodology you're going to use, if you're going to use it, right? I've worked on a couple of the structural equation modeling problems, path analyses, multivariate regressions, and I'll be honest with you, they're very complicated. They have a ton of assumptions. Rule of thumb is, the more complicated the statistical analysis, the greater the assumptions. And usually it takes a lot more time to check out the assumptions than it does to run the actual test. But again, if you're doing anything out of the ordinary, make sure that somebody on your board knows and are okay with it. Did you use any non-parametric tests? Okay, non-parametric tests is if your data is too screwed up, or if your data is ordinal, right? You're supposed to use the non-parametric comparison tests, right? Instead of the t-test and the ANOVAs, you would use like the Mann-Whitney U-test. I believe there's a Wilcoxon test. But, non-parametric means they don't use the means or the standard deviations. That's all it means. So if you're going to use one, make sure, again, your board is cool with that. Non-parametric tests are not considered as strong as their parametric counterparts. Okay, say that again. Non-parametric tests are not considered as strong as their parametric counterparts. But it's been my opinion that it really doesn't matter which way you go. If you use a parametric t-test, for example, and it's significant, the non-parametric version of the t-test, 99 times out of 100 will be significant as well, okay? So, but just check with that stuff. All right, moving on. Now, if you're going to use mediators or moderators, right, those are variables that influence the outcome of your difference test or your relation test, whatever you're doing. And, of course, covariates and the dreaded confounding variables. And if you're going to use them in your study, you got to tell the reader why, right? Why are you going to use these variables, right? Because we know that these all affect the results. Now, some of your hypotheses, you'll be trying to label a mediator or a moderator, right? And then with covariates, that just means you're controlling for a variable. Example, like you're controlling for age or something. And a confounding variable is data that you've already collected, but you didn't use in any of the actual analyses. Again, that could be something like age or gender or something like that, okay. And then after running those tests, you got to tell your readers, how are you going to interpret the results? In other words, which of the following are you going to use to prove that something is significant? You can do confidence intervals like they used to in the old days. Same thing with critical test statistics. You would look up a value in a book somewhere, but we don't teach that anymore. And confidence interval, they've kind of gone the way of the dodo. We use probability values, p-values. So if the p-value is less than 0.05, normally we get to say that there is a significant difference or relationship or whatever you're looking for. We tend to stick to probability values. Some will ask for odds ratios. Those are your logistic regressions have odds ratios. Chi-squares can have odds ratios. And discriminatory function analysis, DFA, also has odds ratios. Again, but just tell the reader how you're going to interpret the results. And tell us which software program you use. When you ran your analysis, which program did you use? We tend to use SPSS. But believe it or not, a lot of the stuff that you could do in SPSS, like your t-tests, ANOVAs, regressions, correlations, you can also do in Excel under that data analysis tab, right? That's relatively new to me, but it's probably been around 100 years. But there's other ones. There's like Stata. There's R. There's MATLAB. There's a bunch of other different stats softwares that you can use. Just let us know which ones you're using. And then you should restate your questions, right? What are your research questions and your hypotheses? The same ones that you wrote in your chapter 1 or chapter 2, right? That does not hurt. Restate your main questions. What are you looking for? And coming to an end here, you got to watch out about running too many tests. So if you run too many statistical analyses, you should apply something that's going to correct your alpha. This is what we call family-wise error rate and experiment-wise error rate. Family-wise is basically if you make a correction, we call it a family-wise error rate. If we don't, if it's regular, p is less than 0.05, that's an experiment-wise error rate. So let's not go there. But good example of this is I had a student, she had 50 different questions that had an answer from 1 to 5, and she wanted to compare to see if there was a significant difference between the male answers to the female answers. So she ran 50 tests, 50 t-tests. You got to remember, 50 t-tests, 95% of them should be accurate, but there's always that 5% rule, right? The type 1 error rule, that they're going to be wrong, right? The results will be inaccurate. So what you have to do if you run too many tests is, it works like this. You should run as many tests as there are groups minus 1. So if you're doing it against a variable with only 2 variables, let's just pretend gender's only 2, you can run 1 t-test before adding some kind of correction. Now the main one we use down here is the Bonferroni error correction. Pretty basics. You take the number of tests that you run. So example for my 50 question person, you would take that 0.05, the original alpha, and then divide it by the number of tests that you ran. So 0.05 divided by 50 comes out to be, I had to do that one on a calculator, 0.001. So only those results that had a p-value less than 0.001 would be considered significant. That's how you control for making type 1 error, okay? So if you run too many tests, apply a correction. And I think that's about it. Let's go to the next page. Yep, we're done. So I hope this helps. And again, I think this is probably the most important thing out of this whole series. Keep on keeping on. All right, MGZ out.